So good afternoon to all. Myself Anil Kumar. I'm again present on the next day, this second day of this course. And today, as listed, the title what I'm covering is satellite-based navigation systems. For the recap, if you recall, yesterday I talked about introduction to satellite-based navigation systems, or in short, we can say introduction to navigation. In that, I covered what is GPS, Global Positioning System, and in that I started very basic understanding of positioning system. I talked about using positioning system where we are recording the attributes of different landmarks coming across, and if you follow these landmarks in a sequence, we can get the path to come back to our campsite. This system works fine for small area, but when we are traveling for larger area, we may have thousands of landmarks. It is very difficult to keep track these landmarks. Second positioning system was the star age. When people were moving on the water surface, they can't see any landmarks on the water bodies, on the lakes, or mainly on the sea, or in the some canals if they are navigating. So they have looked upon the natural stars and planets, and using the astronomical observations of the stars and planets, they were able to calculate their position and time. Third was the radio age, when people were able to develop some electronic system where they can communicate, they can talk, and they can receive the data. But the positioning people have used this radio age system to calculate their position. If they can lock the simultaneously signals from 3 antennas, so that can intersect at one point, and they can pinpoint the position of the person. And fourth one was the satellite age, where the natural planet concept of star age was replaced with the artificial planet called satellites, and on these satellites they have mounted the radio age antennas. So signals are coming from the top, from the space, and if simultaneously signal is received by three satellites at a point, so they can calculate their coordinates. There, I just also concluded for 3D observation, we require minimum 4 satellites. For 2D observation, that is XY or latitude, longitude, we require minimum 3 satellites. Why 1 extra satellite? Because we have to solve the unknown parameter for clock synchronization. That is basically time error has to be calculated. So then I covered and given you the comparison between GPS, that is global positioning system. Globally, it is valid. You can use it anywhere, anytime, in any weather conditions on the globe. And from there, I talked about GNSS, and then I've given the difference between GPS and GNSS. While using GNSS, you may get much better accuracies always, whatever time you are doing observation, because you have very large number of satellites available from different constellations. Even though if you are working in a very narrow lane in an urban area, where their chances of getting satellites from a single constellation will be very less, or if you are working in a deep gorge or in some hilly terrain, where again the number of satellites chances are very less. But if you try to use GNSS receiver, you may get 4 or 5 constellations satellites, and you can lock a large number of satellites. With that, the chances of getting geometry of the satellites is very good. Once the geometry is very good, that means satellites are well distributed in my area. Always, it is not that morning the distribution is good and in the afternoon distribution becomes poor. Always the satellites distribution is very good. That means always the moment the distribution is good, the geometry of the satellites is very good. That means the indicators on the screen, PDOP and other variables we'll see in the coming lecture, is low. That indicates the accuracy in my data is very high. So that is the advantage, and that way I think you got some feel the difference between GPS and GNSS. Today various satellite-based navigation systems available. If you see from starting, the first system, the satellite-based navigation system was GLONASS. This system, they have kept to be around 30 satellites, and this is from USSR, nowadays under Russia. And the second satellite constellation is from USA called Navistar satellite, but from here we got very common term GPS. This constellation required 24 satellites minimum, and nowadays 31 around are working. Then European country and the ESA, European Space Agency, has developed one more their own navigation satellite system called Galileo. In this constellation, we will see there are 27 satellites are required. They are all global positioning systems. And fourth one is from Compass. Now it is called BeiDou. Chinese one, initially it was developed regional concept, and now it has been taken to further extend as a global positioning system. And here you will see combination of 30 global satellites and 5 regional satellites working in this navigation system. Then in the world, 2 countries has developed the regional system called QZSS, Kasi Zenith satellite system, and by Japan, and IRNSS Indian regional navigation satellite system by India, which works with 7 satellites. They are going to expand for 11 satellites. QZSS Japan has on just three satellites, 1 extra, and it is working only for their own country. Now let's see these systems one by one. If you talk about Navistar satellites, navigation system developed by USA for their initially defense vehicles, maybe on the water, on the ground, or in the air for navigation purpose. But today, if you see the GPS, or today we talk about GNSS, it has n number of applications. It can be in civilian purpose, n number of applications people are using, and they are initially, as I told you, they are developed for defense purpose. But today in civilian, in any application, you can see normal fleet management. If you are traveling from one city to other city, nowadays in the mobile phone, that is smart mobile phone, and you have a GPS tool, just you invoke that tool, it will guide you by which road you have to follow. Accuracy is very good. It will give you, it is voice guided, it will go on prompting you have to take left turn or right turn and so forth. So the technology of navigation has become so easy. Nowadays, a lot of infrastructure development is coming up. We get lost which road we have to follow, even though we are acquainted with the city, but so much changes are coming up with respect to road and bridges or the flyovers. So with the help of these technology, we can easily navigate to the updated database. We can use it and we can navigate in the different areas without asking to somebody which road is going where. So if you talk about Navistar satellite, which is under USA as a full their own system. Here you can see a large number of satellites. You can take any navigation satellite system. It is not a single satellite like in the case of remote sensing or any other technology or meteorological satellite. Just one satellite is enough. But here we require minimum 4 for 3D observation and minimum 3 satellites for 2D observations. So, or anytime, anywhere, in any weather conditions, if you have to work, then we require large number of satellites, so that anytime, anywhere we are, we should get minimum 4 satellites for 3D observation. So here you can see in this Navistar system, 24 satellites minimum are required to work fully anywhere, anytime we can do observation. So how these 24 satellites are kept? There are 6 identical orbits. So in 6 orbits, 24 satellites are kept. So each orbit has 4 satellites. 4 into 6, 24. So 4 satellites are there in each plane or in each orbit. All orbits are identical orbit. The altitude of the orbit is 20,200 kilometer from Earth's surface. You can add the Earth radius of 6,000 something. So it becomes 26,000 kilometers from center of the Earth. Inclination of these orbits from equator is 55 degree. So all orbits are inclined at an angle of 55 degree. These satellites are not sun synchronous or geostationary. They are in between. You can see the altitude is around 20,000 kilometers. So from the diagram itself, you can make it out. Each orbit, if you try to see here, one satellite, then one, and then one. So in each orbit, you may get 4 satellites, right? But nowadays in this constellation, there are 31 satellites. So 24 plus 31, you have 7 satellites extra. So these 7 satellites are used as spare satellites in different orbits. So if suddenly some satellite become out of order, they can't replace it, they cannot rectify, they cannot correct that error in the satellite, and so satellite becomes out of control and it is not giving the proper data. So immediately they replace that satellite with the existing satellite in that same orbit. So that's the objective of keeping spare satellites. You can see when you work with the GPS receiver or GNSS receiver, you can see the constellation of Navistar satellites. In there, graphically it will show how many satellites are available and how many satellites you have logged in your area. So here you can see the orbital separation of each orbit with the neighbor one is 60 degrees, 60 into 6, 360. Orbital radius, if you see 26,560 kilometers from Earth center. Orbital period, each satellite takes around 11 hours, 57 minutes and 57.26 seconds. The orbital velocity, that is angular velocity, if you see it is 3874, 3.8 kilometer per second. So that is a huge velocity, the orbital velocity. You can, I think in the 12th class, if you recall, according to the radius, the velocity changes, and same way here at 20,000 kilometers from Earth's surface. Any object which is revolving around Earth will have the orbital velocity of 3.8 kilometer per second. So you can just see this is Earth and I want the coordinates of this point. So I have to lock the satellite 1, then a second satellite, and then third, and then fourth. So minimum 4 satellites are required because I want the coordinates of this point. That means I have 3 unknown variables, x, y, z, and you have one hidden variable. Why hidden? Because in the mapping we don't use the hidden variable, that is time, and that is clock synchronization error. But there are so many applications where people want to run the all the machines with the common time. So 4th variable is time, which has to be synchronized. Synchronized means here the receiver which we have on the ground using the quartz clock, and the satellites which are there in the space has atomic clock. So atomic clock can give time of say 10 to the power nanoseconds, 10 to the minus 9, and here up to milliseconds, say 10 to the power minus 3 seconds. So both clocks gives different times, so they require synchronization. So in place of putting atomic clock in a GPS receiver will become very bulky, very costly. So that is not feasible. And since this system requires large number of satellites, so in place of putting one atomic clock in a receiver, we can directly use the 4th satellite to calculate the 4th unknown parameter, that is time synchronization or clock synchronization. So we can synchronize both the clocks once we log the 4th satellite. So that way this system works. For USA based system, if you see ground control segment, it has one station at the on the Earth at Colorado Spring, which is working as a master station as well as monitoring station. Master means it sends the data to the satellite to rectify the problems in the satellite or to maneuver and bring the satellite to the defined orbit. Because there is electromagnetic flux and that disturbs the satellite to remain in the same orbit, and it start deviating from moving away from the orbit. So maneuvering has to be done timely on different times, and that is the use of working a station as a master control. This is working as a monitoring station also to monitor the health of the satellite. It is moving in the defined orbit, all the components of the satellite is working properly as per the design, and then other islands which are under USA are working as a monitoring station here. And you can see these islands are well distributed, and they have chosen such a way that the same satellite in a day can be monitored by different stations. So every say few hours they can get the health of the satellite, and if some corrections are required, that information is passed to the master control to correct that error present in the satellite. Next one, if you see GLONASS satellite, which is basically Russian, USSR initially, and now it is under Russia. This is the first navigation satellite system globally they want to develop so that they can monitor their defense vehicles. That was the first application for navigation purpose. They want to navigate, they want to guide, they want to see where their vehicles are on the ground, in the air, and on the water surface. So this was the first system. And if you see its properties, it's about more details. GLONASS space segment consists of nominally of 24 satellites. Again, it is identical to Navistar satellites of USA. It is distributed over 3 orbital planes. So these 24 satellites are not distributed in 6 orbital planes. Here, they have only 3 orbits. So 8 satellites are there in each plane. In each orbit, there are 8 satellites. Each satellite is identified by its slot number. There is ID number of the satellite, which defines the orbital plane and its location within the plane. So where that satellite is in that orbit, so that is defined by its slot number. GLONASS satellites operate in circular orbit, so all the orbits are circular at an altitude of 19,001 kilometer, 19,100 kilometer. That's altitude, so it is little lower end side compared to USA based satellites. Each satellite complete the orbit in approximately 11 hours and 15 minutes. So you can see the USA based satellite was taking around 11 hours and around 57 minutes, but this one is taking less time because that means it has more higher orbital velocity. It is just taking 11 hours and 15 minutes. So you can see the distribution of the GLONASS satellites as a space segment. There are 3 orbits, and there are actually 8 satellites, but they keep 1 satellite extra. So it is 24, and they have kept one satellite extra also in the orbit. So just by 3 orbits, the system works very nicely. Globally, anywhere, anytime, we can use the system to get the coordinate. More or less, it is now presently fully operational with around 24 satellites. So this is the distribution of the ground control station for GLONASS in the Soviet Union. If you see the complete as a Soviet Union, so you can see the distribution of different monitoring station which monitor as well as they control also. But they have, these are the major, but they have other stations in other areas of the globe, but these are the major stations near to the Russia and USSR country. Then third one, if you come with the Navistar system, navigation system, which was developed by European Schengen countries, called Galileo, and it is basically controlled by ESA, European Space Agency. So Galileo, if you see its property, is a global navigation system or global navigation satellite system that went live in 2016. It is more or less getting fully operational. It is created and developed by European Union through European Space Agency, ESA. The first Galileo test satellite, the Globe A, was launched in 28 December 2005. That was the first satellite as a test satellite was launched. And the first satellite to be part of the operational system was launched on 21st October 2011. It was making the system to be operational to start getting the coordinates. And by July 2018, 26 of the planned 30 active satellites were kept in the orbit. Full Galileo constellation will consist of 24 active satellites, which is expected by 2021. So in this year, as per schedule, if they are moving, they may be able to achieve to insert all 24 satellites in the given defined orbit for Galileo system. next generation of satellites will begin to become operational after 2025 to replace older equipment. So what they will do after 2025, they will be start replacing the older satellites, because generally these satellites has life of 10 to 12 years. Galileo, further if you see, by early 2020, there were 26 launched satellites in the constellation, 22 in unstable condition, 2 satellites were in testing, and 2 more not available for users. Out of 22 which were active satellites, 3 were from IOV in orbit validation types, and 19 of the FOC full operational capability type of satellites. There were 2 test FOC satellites are orbiting the Earth in highly eccentric orbits. They were not the circular orbits, whose orientation changes with respect to other Galileo orbital planes. So you can see the characteristics of this system. It has different level of orbit. It is not just all circular orbit. The Galileo system has an accuracy of less than 1 meter when using broadcast ephemeris, and 1.6 centimeter when using real-time corrections for satellite orbits and clocks. Further if you see the Galileo satellites of European Schengen countries, Galileo has 3 orbital planes spaced with 120 degree with each plane, 9 active satellites plus 1 spare satellite, for a total of 30 satellites are there in this system. Galileo satellites operate in an orbit of 23,000 and 2,200 kilometers at an inclination of 56 degree. The orbits are inclined from equator. Orbit is higher in altitude and inclination than that of GPS. Here if you see its orbit, there it was 20,000, and here it is 23,000 kilometers and 222 kilometers. So this is more higher than in comparison to GPS orbits satellites, and it is more higher than GLONASS also, because GLONASS was just 19,000 something, and Navistar satellites were around 20,000. So this is 23,000 around. BEDU, which enables Galileo to provide service at higher latitudes and more accuracy. The advantage of keeping higher altitude in the Galileo is, when we are doing observation at very high altitude, still we get data with very high accuracy. So here you can see the Galileo space segment, 3 orbits, and each orbit has 9 satellites and 1 spare satellite. So with this combination also, they are able to cover the complete globe. And you can see this is the Galileo ground receiving station worldwide. You can see they have different stations which are working as a monitoring at the master control. So objective again is same. Monitoring station goes on monitoring the satellite from different corners of the Earth to check its health and receive the data, and that data is sent to the master control to apply some corrections if required, and if not, then they declare the satellite dead. And for the dead satellite, they give the replacement. And that's why in the orbit they keep some spare satellites, because immediately the replacement cannot be kept, cannot be launched. So initially, for time being, they just use the extra satellite present in the orbit, and later on they eject the more extra satellite in the same constellation, so that they always have some spare satellite. The fourth one, if you come, the BEDU satellite, which was initially called Compass as a regional satellite, but now it is a global satellite system by China. It consists of 2 separate satellite constellations. So it is not a single identical orbit. It has 2 separate satellites which are working in totally different constellation. The first BEDU system, officially called the BEDU Satellite Navigation Experimental System, and it was basically at the experimental stage from Compass to BEDU, and now also known as BEDU 1. So they have different level of BEDUs, 1, 2, 3, 4 like that. Consisted of 3 satellites, which began in 2000. The second generation of system called BDO-2, officially called BDO Navigation Satellite System BDS, and also known as Compass or BDO-2, become operational in China by December 2011 with a partial constellation of 10 satellites in orbit. Then they have first BDS-3 satellite was launched on 30th March 2015. And by 27th December 2018, BDO Navigation Satellite System started providing global service with the maximum number of satellites, and final satellite of BDS-3 was launched into orbit on 23rd June 2020. It was said in 2016 that BDO-3 will reach millimeter level accuracy with post-processing data. So once we do post-processing, by BDO-3 data, we can achieve millimeter level of accuracy. So here you can see the constellation of BDO. It has basically geostationary satellites in the geostationary orbit. It has a medium Earth orbit MEO satellites. It has IGSO, inclined geosynchronous orbit. So in the BDO, there are 3 level of orbits. You can see here it is geostationary orbit. Then here you can see geosynchronous orbit, IGSO, and here you can see the MEO, medium Earth orbit. So 6 orbital planes are there. 5, so total 35 satellites they have kept, in which 5 are geosatellites, 27 are MEO satellites, and 3 are IGSO satellite. They are inclined at 55-degree inclination. Altitude, if you see, it is 38,300 kilometers for geostationary satellites, and for medium Earth orbit satellite it is 21,500 kilometers. So these are BDO space segment details. And next, if we come to so these were the 4 global navigation satellite system I talked about. Coming to the regional systems, like for India, it is called IRNSS, and yesterday it was asked also NAVIC. It is in a common layman term, it is called NAVIC, basically to guide the boats for the fishermen. So anyway, this is a regional system, so it is working for India and its region. You can see its range is covering like this in this area. You can use it for getting the coordinates. So 24 hours this is available in this region. So it is region based positioning system. It is not working globally, but it can extend for globally. But the way it has been designed, because the navigation system is basically satellite based navigation system, is a costly affair. It is difficult to maintain huge number of satellites when you have to cover the complete globe. They have thought for defense purpose as well as for civilian purpose by Indians, that we don't have to cover the complete globe. We have to cover our own territory and the India to provide the defense and the civil services for positioning system. So that way they have developed the regional based navigation satellite system. Here if you see, initially there were 3 satellites are there in geostationary orbit. So here you can see this one, and this one. 5, 6 and 7 are the geostationary satellite exactly on the equator, and then 4 satellites are geosynchronous. So here 1, 2, 3 and 4. So 4 satellites are geosynchronous. Geosynchronous means they are making some angle. So geostationary means they are not making angle from the equator. The altitude is same, 36,000 kilometer, but they are not making angle. The geostationary are having 0 inclination with the equator. But if you see geosynchronous satellites, they make angle of around 23 degree. So if you project these satellites movement on the ground, the foot movement, if you see on the ground, they appear like 8. So here you can see they are making 8 here on the ground. If you project this on the ground, it appears to be like 8, their movement in the 24 hours duration. In future, presently there are 7 satellites, but they will go for 11 satellites, few extra as a spare satellite, so that if some satellite is not working, so they can replace that with the spare satellite. So that way they will extend up to 11, but 7 is maximum for getting the coordinates nicely, 24 hours anytime in the Indian region, and 3 they will keep as a spare satellite. The second regional system which was developed by Japan, it is called QZSS. QZ means quasi-zenith. So satellites are exactly at the top. That's why it's called quasi-zenith satellite system. Satellites. So QZSS use one geostationary satellite. So in this constellation, you have one geostationary satellite. You can see this pink line in this. There is a geostationary satellite, which is exactly on the equator at 36,000 kilometers. And 3 satellites are tundra type, highly inclined, slightly elliptical geosynchronous satellites. So if you see other orbits, this yellow one and this red one and the blue one, cyan color, they are tundra type, highly inclined, slightly elliptical geosynchronous orbit. Each orbit, these orbits are at an angle of 120 degree apart from each other, and because of this inclination they are not geostationary, but they do not remain in the same place in the sky. You can see these orbits do not remain in the same place if they are designed such a way, and presently you can see in these graphics how these orbits are coming up. 1 geostationary and 3 inclined geosynchronous orbits, total 4 orbits. So in this total, 4 satellites are working, and they appear like a quasi-zenith way, so that 24 hours they can monitor the Japan and its surrounding areas. So if you see their signals on which frequency these systems are working for the QZSS, it is using L1CA, that is 1575.42 megahertz, used for combining with GNSS to increase the availability of PNT, that is for positioning, navigation and timing services. Second is L1C, it is again using frequency 1575.42 megahertz, used for combining again with GNSS, and it increases the availability of PNT. Again, PNT is a positioning, navigation and timing services. Then L2C is using frequency 1227.6 megahertz. It is again used with combining with GNSS and increases the availability of PNT. It is using L5. It is again, the objective is to increase the accuracy of PNT services. Then it has L1SAIF frequency, which is giving sub-meter class augmentation of the system with the GPS based SBSS facility. So it is augmenting the system to increase its accuracy. Then LEX, again working at 1278. It is experimental signal for high precision service compatible with Galileo and E6 signal. You can see the graphical distribution of these satellites on the ground. If you see QZSS satellites ground track, it more or less appear like 8, but not exact 8, but you can see the path is following like this, because the way the orbits has been designed and kept in the space, when you project the movement of the satellite on the ground, it appears like more or less like this type of shape. So this is all about today, talking about satellite based navigation systems. I talked about initially 4 global satellite based navigation systems developed by different countries, by Russian, by USA, by European countries, by China, and then 2 regional systems, like one by India and second by Japan. You can see the maps. Previously the topographic maps were covering as a regional only. The topographic maps developed by India long back by Britishers and then later on modified by Indians, they are basically covering the region only. The one topo sheet or the complete data man, the coordinate system which is used, which is working only for the region, India and its surrounding up to India, Pakistan, Bangladesh, Myanmar, Sri Lanka. So this was the region they were working, and with the same concept, just to keep the satellite based positioning system to cover our own territory and the surroundings. So they have gone for regional based system, but other countries, they were able to manage to make the system from regional to global. So they have developed the global navigation satellite system. So because these systems are very costly, they does not work with a single satellite. Minimum 4 satellites are required. We will see in the coming classes why minimum 4 mathematically, and why not just 1 satellite, right? So all these things we will see in the coming slide, in the coming lectures. So today I just talked about satellite-based navigation satellite system. Tomorrow we will have the lecture on GNSS measurement and positioning techniques, where I will talk about what are the measurement techniques we have to go for to get our coordinates, and why minimum 4 satellites are required for 3D observation or 2D observation. Why minimum 3 satellites? And then positioning techniques. This is really practical issues when we are doing actual measurements. So what are the different positioning techniques we can adopt for getting our coordinates? So thank you all for listening, and now I can wait for your questions. I hope if you are dropping the questions in the chat box, so I can easily read. Like yesterday, it was easy for me to pick up the questions. I'm just waiting for a few minutes to start receiving your questions. Thank you all for listening. The second lecture in the series.